Hello dear students, today we will be discussing about earth resistance measurement. So earth resistance is defined as the resistance offered by the earth electrode to the flow of current into the ground, and resistance simply implies that it is a resistance between electrode and the point of zero potential. Now the value of earth resistance will be varying from point to point, and at certain areas like in large power stations, the resistance is in the range of 0.5 ohms, and in most of the power stations you have 1 ohms, and for small substations you have 2 ohms, and in other cases or in general cases we have 8 ohms. So this is a range of resistance that is expected at the end of the experiment or end of the resistance measurement process. Now earth resistance, the first term that we need to understand is the resistance area or potential area. So it is the region around which the earth electrode is driven. So we make the measurement by using or by driving earth electrodes into the ground. So the region around that earth electrode which is driven into the ground is known as the resistance area or potential area. So it is known as a potential area because it is at this related to this point that we measure the potential between two different points across the ground or across the earth. Now the resistance of the earth that we measure depends on few factors. First one is the shape and material of the electrodes that are used. So that is one of the factors. You can design electrodes in different shapes and based on different materials. So in each case the resistance that is measured will be affected depending on the electrode that is being chosen. Then it also depends on the depth in the soil at which the electrodes are inserted into, and it also the resistance also depends on the resistivity or specific resistance of the soil surrounding the electrodes. So the resistivity further depends on the type of soil and the moisture content. Now we make use of a method which is known as potential fold method. So in this potential fold method, the resistance area, as we have already defined, it is the area around the earth electrode where the voltage gradient is measured, or the change in voltage is measured. So the voltage will be, once you measure the voltage across 2 points, the voltage will be varying with respect to distance from one of the electrodes. So that region is already defined as the region around the electrode, which is known as resistance area or the potential area. Now in this potential fold method, there is a reduction in potential from one point to another point, a change in potential from one point to another point. So we make use of an AC source, and based on that we send alternating current of a steady state value or a constant value passing through the earth path from E to A. Okay, from E to A. E is the earth electrode under test that is being driven into the ground. A and B are auxiliary electrodes. These are positioned away from the earth electrodes so that their resistance areas do not overlap. So A is farther away from E and B is located somewhere in the halfway between E and A. So we have 3 electrodes, and B1 and B2 are the different positions of B. I mean, we will see that we will be making use of 3 positions to arrive at the result. So this one of the position is B, then we will move to B1 and later to B2 to take 3 set of readings. So that's how we measure the earth resistance. Now the voltage, the current is being passed from E to A, and the voltage is measured from E to B. So we have a voltmeter connected. So what you can see is that your current path will be something like this. Your current path will be something like this. So this will be your current path. Okay, and you will be measuring voltage across these 2 points. You will be connecting voltmeter across this. So you will be measuring voltage across these 2 points. So this is how you take the make the connections and take the reading. So this is the practical case where you have a instrument available and which is used to measure the earth resistance, and that the leads are directly connected to the earth electrode. So this is the earth electrode that is made of copper, so that is driven, and then you have two auxiliary electrodes. One is the outer one, which is termed as A, and B is the inner one. So we connect everything, and then ultimately the resistance is being marked. So here the resistance is indicated as 10 ohms. So the resistance will be varying depending on the position of your, depending on the nature of the soil, depending on the location of where you are taking the reading, etc. Again, it also rocks that are available. If you are measuring the resistance in a rocky region, then the resistance will be higher. So in that way, resistance will be varying. Now the current density, we can see that the current is varying from E to A. So the current density will be higher at the vicinity of the electrodes. So if your current is flowing from A to E, the current will be density will be higher at this point, because this is the original point, and the current will be spreading out, and then it will be further reaching at this point, and it will be converging at this point. So here there is a divergence at A and convergence at E. So you can see that at the middle region the current density is almost same in almost all the area. Also the potential also varies from E to A. So as we move from E to A, so this is point E, and as we move from E to A, the potential also varies, and we can see that the potential is almost constant at the middle region where we are trying to place our electrode B. So this is the region where we are trying to place our electrode B, and this region is, so this region is E, this is B, and this is A. Okay, so as we move away from E, at some distance away from E, you will have a constant potential, and further the potential will be changing as we move away from E to A. So that's how the potential distribution is there, or voltage distribution is there between the earth electrode and the auxiliary electrodes. Now how do you measure the earth resistance? Now we have already provided provisions to measure the voltage drop between E and B. So you have a voltmeter available here, and also current through the earth path between E and A is measured with the help of this ammeter. So once we have voltage and current, resistance is provided by the equation V by I. So it's a simple process. Now what we do is that once we get one value of Re, we move the earth electrode, or the auxiliary electrode B from the first position to a new position B1, which will be a little far away from B, so that the resistance area do not overlap. So it is little far away, say 5 meters from B, and we take another set of reading, and again then we will move the electrode B to the opposite direction, again little far away from the initial position, and we take the third set of reading. In all the cases you will be getting the value of Re, and what we can see is that if you are placing the electrode accurately, you will get approximately the same value of Re in all the three cases, and the average value will give you the earth resistance at that particular point. Now so the resistance can be obtained in such a manner. Now what we do is that if we change the position of B, that is the auxiliary electrode B, from the point E to A, and we measure earth resistance continuously, and that can be plotted, the value for Re can be plotted, and you will be getting a graph like this. What you can see is that what you can infer is that the measured value of resistance Re depends on the position of auxiliary electrode. So once the auxiliary electrode is close to E, what you can see is that the resistance is rapidly rising once you are in a region which is close to E. Here your current density is also higher, so you can expect a lower resistance here. So your resistance is lower and will be further increasing, and once the current density is constant, you can expect a constant resistance at this region, and you also have a constant potential in this region. So you can expect that here, and later your resistance will be further changing towards the point A. So in a middle region you can see that between E and A, at a certain region you will have a constant resistance, and we will be measuring the or will be positioning B in such a way that you are measuring the resistance of this region. Okay, and this value is taken as the earth resistance. Now the spacing between the auxiliary electrode B and the earth electrode E should be large to get proper results. So if you place B somewhere here, you may not get the proper result. So it has to be somewhere in this region to get accurate values of earth resistance. So that's how the earth resistance is defined. It is a constant value between these two electrodes. So that is taken as the earth resistance of that particular area, or earth resistance at which your electrode is being inserted. So relative to that, the earth resistance of that area can be considered as the value Ra obtained by keeping the electrodes in such a halfway between the electrodes E and A. So that's how you measure the value of earth resistance. Thank you.